Good morning, Dallas. Good evening, India. Good evening, Bangalore, the Silicon Valley of India. I could say that welcome to the Global Electronics Friday talk show that is based on electronics manufacturing, what's happening in the electronics manufacturing world in the world. And I'm not limiting myself to only United States or North American market or Southeast Asian market or the European Union, but I'm actually addressing the global electronics manufacturing trend. What are the challenges faced? What are the developmental activities happening? What are the technologies employed and will be employed in the future? So those kind of talks will happen on this platform. And this is your host, Rajiv Kulkarni, based out in Dallas, Texas. Current time is 9:30 a.m. in the morning. And in India, it is 8 p.m. Why I'm talking about India? Because we have a guest from India, as you already know, because we publish the guest name and the details of the topic talk or the talk theme every week through our poster as well as our YouTube link. We give the description there. So let's talk about today's guest. He is a great designer. In fact, he was there with us last week as well. He's a great designer, PCB design, or anything to do with electronics design for the last 3.5 to 4 decades in the Indian electronics industries. He has been in various roles in the different electronics bodies, working as an instructor, working as a CID, and working as, holding a different level technical positions in the electronics bodies. And he has given many papers in the electronics world, whether it can be the events happening in the stateside, events happening in the East Asian market, or in the European market. And also in India, he has given many talks. Many means it's uncountable, I would say. Ladies and gentlemen, let's welcome the veteran Mr. Amba Prasad from Bengaluru, which is also called as Silicon Valley of India. Welcome to the show, Amba Prasad, once again. And how are you doing this evening? You can unmute now.
Thanks for the great introduction. Whenever I gave a speech, people wanted to be extempore only. That's the demand people. They told you talk instantly. That has got a more impact. Yeah, that's what it was. Yes.
That is the beauty of Mr. Amba Prasad. Let me tell you, ladies and gentlemen, because you give him any topic, he can speak on that, and he will speak very impromptu. I mean, he doesn't prepare. Of course, yeah, if there has to be any preparation to be done, then he will prepare the slides and so on and so forth. Because I myself have worked with him in many such incidences where I being the president of SMTA body, which is Surface Mount Technology Association out of India. And so where he has given a lot of, he has been served under as a technical program director. And then he has given many technical papers there. And he gives very instantly, he has answers for all your questions. And today's topic, let's come there. We are talking about signal integrity. What is signal integrity? The importance of signal integrity in complex PCB design. How do we measure signal integrity and so on? So let's have a interesting discussion with Mr. Amba Prasad. Amba Prasad, let's have our question and answer sessions. And of course, people are waiting for you, to listen to the wealth of, the knowledge that you're going to share on signal integrity today. And as we all know, that any product to happen, the design is the most important factor, because without design, no product can, born itself. So, Amba sir, first of all, what is signal integrity?
Yeah, you reminded me 3.5 decades of experience in PCB design and product design. Actually, we were implementing, at least our generation implemented the signal integrity Even before the name signal integrity was coined, actually.
Oh,
There were always people worried about the spacing and the trace length and the
mhm.
return. So, in a nutshell, these three, if you maintain properly, you will achieve signal integration.
Wow. So, so when you said, like these three parameters is achieved, then we can definitely achieve the signal integrity. So how the role of signal integrity, or what is the role of signal integrity in the PCB design?
So basically, if the slides get forwarded, if you can go to slide number 3, uh, let's show how it works like. Yeah, next slide. Yeah, here I have shown a typical multi-board system which is sitting on a backplane. The driver sits on one of the PCBs, and the receiver can be on the same PCB or it can be on some other PCB across the backplane. Now the signal what we launch on the one of the PCBs has to travel the entire length. It has to come out of the component, come through the component leads, then go through the traces, go through the wires and the connector, travel in the backplane, and it has to enter. Again, the path gets reversed. It enters through the connector, it goes to the traces, it goes to the package, it goes to the receiver IC. This is called as a forward path.
Okay.
As the signal is traveling, at the very instant, the return path has to be defined actually. So if these two are defined properly, you will not get into any signal integrity problems.
Oh, okay. So, I mean, this is basically the role of signal integrity in the PCB
Yeah.
design, typically.
And what I have shown is a typical multi-slot backplane. This problem can happen even in a system with the 2 cards or system with a single board form factor also. And this same thing will happen in an aircraft. Aircraft, for example, some signals are very close to the pilot, and some signals are elsewhere. And also the passengers are enjoying the entertainment electronics. No, all this. But as a system, the concept remains the same. You have to
Okay.
launch a signal. You have to receive the signal at the receiver with no distortion within a specified time, and the return path has to be defined, and it also has to return within a specified time. If these two happen, no problem. That is signal integrity.
Excellent, excellent. So at what point do you think the signal integrity becomes a problem, and how do we stop it?
Yeah, you can just go to the next slide.
Yeah.
So here we are showing signal speeds on the y-axis and PCB trace spacings and the component pin spacings on the x-axis. As we know, Rajiv, since so to say 1990s, speed is increasing and the trace widths and gaps are decreasing.
Mm-hmm.
Also, so what happens is when we launch a signal, the signal has got 2 lengths. One length is called as a critical length. That is the signal rise time and the propagation delay. The signal will complete one cycle. Okay.
Okay.
Within it completes the cycle, if it reaches the destination, then there are no reflections. There are no distortions. But sometimes it is very difficult to achieve. So then it has 1 or 2 reflections and then it settles. As long as the physical path of the signal propagation is less or equal to the critical path, okay, there is absolutely no problem. You will not see any reflections. And when
Wow.
we say it is the critical length, it starts from the silicon, it goes through the bond wire or even bumps within the package, and then it comes out of the package, and then it goes to the PCB trace, it goes to the fan out, it goes to the via, it goes to the PCB trace, to the connector, to the backplane, or through the cables. So the entire entity it has to be measured. Actually, nowadays, not even nowadays, even last in 2000 onwards, we always measure signal in time. We don't measure signal in so many meters or millimeters or whatever it is. It is measured in time actually.
Correct. Yeah. So how do we stop these things?
Can you go to the next slide? So here I am showing a forward path of a signal, and this is a typical schematic. There is a forward path. You can see the rising edge, and there is a adjacent. There is one more trace, which can be, if it is a synchronous bus, it is a part of the bus, or it can be some other signal. Now these two traces, they see a capacitive coupling, and they say inductive coupling amongst the two, and also there is a reference plane on the bottom. Okay. Now, as long as the signal return path is in the reference plane, now if it sees any disturbance there, the return path will try to find an alternative way. That manifests as a capacitive coupling or inductive coupling. That is where we see noise.
Oh, okay. Interesting. Okay. So now what are the factors, you think, of course, I think it may be a repetitive question, but still I would go ahead and ask, that can lead into signal integrity issues in a PCB design?
Okay. So the faster the edge rate, I mean, people take it as a rising edge or a falling edge, but in many protocols, we call it as a edge. Sometimes a falling edge can be shorter than the rising edge. Basically from say 80 to 90% rise time, or some people will say 90 to 100% rise time, how fast it rises. The faster the rise time, the shorter the length. Actually, the physical length. Yeah, that's one of the key mechanisms.
Wow. So very interesting information, Mr. Amba. And let's take a quick break here and we'll continue our discussion. Good morning and welcome back to Global Electronics talk show here, live talk show. And today we are talking about signal integrity and its importance in the PCB design or the electronics design layout as such. And we have our expert design professional from India, that is from Bangalore, the Silicon Valley of India, Mr. Amba Prasad with us. And we have been talking about the impact of signal integrity on the PCB design as such. And it has been very interesting information so far. Mr. Amba Prasad has given us about what is signal integrity and the role of signal integrity in PCB design, and what are the factors that can lead into signal integrity issues, and also at what point signal integrity becomes a problem and how do we stop it. So Ambaprasad ji, welcome back to the show after this small break. So what are the design consideration you think for improving the signal integrity in the PCB traces?
Yeah, well said. In the beginning, you introduced as an effect of signal integrity on the PCB design.
Correct.
Now the reverse is true. A very a very suboptimal PCB design, not
Correct.
only the physical layout, even let's say the material selection and fabrication factors can influence on the signal integrity.
Hmm.
Okay, though we have done a very good component selection, we have done a very good, I talked about you take care of the length. The length is measured in time. You use a very good CAD tool. But if the compromises are done in the layout, as well as the compromises are done in, say, the PCB material selection and the PCB fabrication, I think in the third part, we talk about assembly also, how it affects even a very good design. These downstream activities can sometimes make it or break it, actually. Okay. So go to the next slide, please. Yeah, here I have given a chart which is publicly available. This chart I have given a signal rise time versus the length. Then again, we talk about the signal length is measured. Signal length by 4 times, length by half, or length by 1/3, length by 1/4. These are all some formulas are available and some critical parameters. Wavelength by say half wavelength, quarter wavelength, 1/10 of a wavelength. These are the factors which we are used to define certain physical entities. And I have given a chart for a single-ended as well as a differential. And when we do certain calculations, we have to take this length into consideration. If we don't see this length as a consideration, let's say 1/10 of a wavelength or half of a wavelength or 1/4 of a wavelength, that comes back as a discontinuity, which causes reflections. So this is very important in PCB design. So having said that, a PCB has been done perfectly because there is some company design rule or some mentor behind you and telling you how to do it. If you go to the next slide, signal integrity drivers I have shown. Next slide, please. See, the length is what we have achieved. There is no problem. And this is like what time shown you in the Google map. In the Google map, it shows it can reach airport in half an hour or 45 minutes. Suddenly, we have to go to the traffic. Maybe the road condition is bad. Or maybe too many passengers are trying to reach the airport at the same time. Or maybe you can say there can be Deepavali or a marriage procession going on there. So similar example I'm giving. In this, there are 3 attributes. One is the copper. The actual copper which we use for the copper traces, that we can compare to the road which you are going. If the road is smooth, travel is smooth. Or if you are going on a tolled highway, you pay the money and you go for it. Okay? Nobody disturbs you. Otherwise, if the road is very rough, you will have ups and downs. And suddenly you find you're 15 minutes late and driver becomes panicky and he tries to drive faster, which is the resistance, and it becomes heated. Then you will never reach it, actually. So that's the problem. And then there is on the extreme left side, I have shown the surroundings, like the media. Contrary to the popular belief, the signals will never travel on copper. Copper guides how the signals will travel. Actually, in a very high-speed environment, the signal propagates as an electromagnetic wave, capacitive and inductive in the media. It travels on the media, between the gap between the trace and the ground plane, between that it travels. So your media has to be clean. The glass fibers have to be very clean. There should not be any defects or air bubbles or suddenly resin starvation and stuff like that. So this affects a lot. Okay. So, and again, on the other side, I have shown the effect of miniaturization, where people try to make ICs and connectors as small as possible. That in turn creates noise. So these are the 3. And these are quite contradictory with each other. Yeah.
So signal integrity is being imposed on pretty much all PCB which goes to different application, or it is only like meant for, high speed, high frequency telecommunication, where you need these kind of, features.
See, the signal integrity, if you look at the transmission line, was a military secret in Second World War.
Yeah.
So the missiles were, or missiles and radars they were using there. But it became a regular industrial term once the World War is over. Okay. Now it is available. Now in the 90s, the signal speed was so low. The critical lengths were measured in terms of meters. Nobody bothered about it. As the signal speed increased, then it became an issue. People started, facing problems. Though their designs were perfect, they started facing problems, and there are fixes are available. They started putting buffers. They started putting cables, guards, guard bands, and all. But if you, in a very classical view, the microwave design and RF design, that is the ultimate signal integrity. But they were there earlier. This came into digital design because as the speed rise and increased, even the digital electronics started behaving like RF effects on that. That's why it became very popular in late 90s and 2000s. Yeah.
So I mean, what you're saying is pretty much signal integrity is there in pretty much all kinds of PCB design.
In all kinds of electronics, yes.
Okay. Because I remember a few years back when I was in the PCB industry. So, there used to be certain requests used to come from customers who were manufacturing very high frequency, product, for example, telecommunication or so and so forth. Only such needed the signal integrity, feature built in their PC boards. I mean, of course, those PCB will cost much higher than the normal PCBs.
Yeah, that is the price. Yeah.
Yeah. Okay.
Earlier, I told you about you have to pay a toll if you want to reach the airport faster.
Yes.
That is
Yes.
the premium you are paying for fabrication, material, and assembly. Yeah.
Correct.
That's
Correct.
exactly so.
Excellent. Excellent. So, what else you want to share with us, Mr. Ambaprasad, on the signal integrity?
I want to share with you that I told you even before signal integrity became a catchphrase.
Yes.
Our team was working on signal integrity. In fact, our team in my previous company was the first company to introduce a control impedance board in India.
Okay.
We still remember that. So if you go to next slide, please. Yeah, this was some sort of a CAD design flow. 1980s. I remember 1980s. Maybe some of the audience were in their schools now.
Schools
but
now.
efforts started then. This was done by a very big company, which does even from a chip up to the systems. In a very big successful company. They did this. They started telling CAD is a must, simulation is a must, control impedance PCB is a must. But even at that time, the signal integrity efforts were about separation between traces and the length matching. They never much bothered about the of the latest. Now we talk about jitter, we talk about propagation delay, skew, and all. These came little later. But in the 80s, you maintain a neat space between an aggressor and a victim, you are done. That was the signal integrity in the 80s and 90s was about only noise reduction. But after 90s, it became length matching, skew control, and even jitter control. It became.
Okay. So we have around 5 minutes left. So anything that you want to add more?
Go to next slide, please. I think I have only 3 more slides. So
okay,
this is, this is where your EDA tools will definitely help you. EDA tools are coupled, they have a signal integrity as well as a CAD. They do online translation and they give you instantly the signal integrity spreadsheet, how it is closure is done. And it is almost online. You don't have to, earlier people used to export and import. Now it is not necessary. It is almost online on the fly. And one interesting slide I have, I think 3 more slides, simulation versus measurement. You can just put next slide. So simulation also, in the 90s, companies used to outsource the simulation. They used to
Okay.
outsource simulation and get it done, both post and pre-layout. But now they do in-house. And in fact, in many companies, it will be a very small team, or even a single person can do it himself. Very interesting take on this. This was told by one of the leading gurus, signal integrity. He says, a simulation is something which the person who did it will defend and he can understand, and nobody else will understand. Because he comes out with a traffic rule and he says, you do like this, you do like this, you do like this. If you
Correct.
argue, you do it or else. Okay? And people will try to implement or not implement it. It is at their own risk. But what you need for signal integrity, you need a very good fundamental knowledge, how the signals behave. And then you need a very good simulation. Then you need a very good CAD practice. And then you have to have a measurement. You need a measurement systems, the signal performance. But here an interesting take on that by the same author. Now the author says a measurement is something which everybody believes, but the person who measured will not believe, because everybody is believing, because once you measure it, once it is within the optimal limit, it converts into automatic sales. There will be no factory recalls. There will be no rejections. So here, the person who did the measurement will burn midnight oil and they'll come out with a value, but everybody else will, in fact, they believe on that actually. And then there is one more slide, which is very interesting.
Sure.
Where we are. There is what is called as a feature size. Earlier, I was telling half wavelength or 1/10 of a wavelength and all. If when you launch a signal from a silicon, you go to the, let's say you go to a wire bonding, or you go to a component lead, you go through a via, you go through a trace, you go through a cable. If these lengths are less than that, or 1/10, let's say a via is less than 1/10 of the wavelength, it causes reflection actually, and it creates a propagation delay. Please go to the next slide. I will just show you. This is very interesting.
Yeah, please.
You will be surprised. This slide, if you see properly, for a 10 gigahertz, okay, 1.6 millimeter is a critical length.
Wow.
Why I'm telling this is, typically, all PCBs are generally, most of the PCBs are 1.6 millimeter. Now, if you do a 10 gigahertz board on a 1.6 millimeter thick board, you route in top and bottom layer, you are inviting for trouble, because your PCB itself and the via structure itself is a discontinuity.
Yes.
Now you have to make the PCBs thinner and thinner. So this is the take. And then I have shown signal integrity cause and effects. Next slide. Yeah, it is a mismatch in impedance, capacitive disturbances, inductive disturbances, and critical signal speed or versus length, propagation delay, switching noise, because we are sending so many signals together, and voltage drop, because signals and terminations, they consume power, and power delivery, manufacturing concerns. Why? Because these individually or collectively will cause reflection, timing issues, propagation delay. They impose a propagation delay, like your Google map earlier. Okay.
Right.
And crosstalk and switching noise. And in turn, all these will together create emissions, and your system, not your system, don't take it personally.
No.
System may fail in see, all signal integrity is not contained. It may manifest as a electromagnetic emission, because even if there is a return path is not proper, the return paths will try to find a path. It may find a path through the adjacent board or adjacent cable, or it can be through anything else. So this will create a disturbance. Okay. So, but signal integrity is one of the weighable and measurable entity. It can be measured actually. Then I have one more slide. That is the last slide.
Very interesting.
And just to put the last slide, please. So I have shown in this how to manage signal integrity. There are teams are available now, signal integrity experts, both externally as well as internally. Strong theoretical knowledge. I will show you how strong it is. Then PDKs and ADKs. PDK means if you buy a chipset, they give you design kits that has to be followed. ADK, if you are doing any code more than 10 gigahertz or 20, 50 gigahertz, even assembly plays a major role. Maybe that can be a separate talk show going forward. Okay, and then your concerns have to be tangible. If concerns are too strict, people will find fun in not following it actually. It has to be very tangible. Otherwise, people will get they don't follow. That's the problem. And manufacturing and feedback from the PCB vendor, he should say they also have huge knowledge. And test and measurement instruments, which is and you know one thing, just because your previous PCB worked, it is not a passport for you that your next PCB works.
Correct.
So
correct.
it's a moving goalpost. As far as theoretical knowledge is concerned, I have a few books I'm showing here. This is called as a transmission line theory.
Hold it on the top. Yeah.
Yeah.
Okay, great.
So
you can read the book,
book title. Transmission Line Design Handbook. This book was published in 1980s. All your signal integrity characterization equations, they come from this book. This book is a classic. Okay. And then this is surprising. A father and son duo, they have published a book called Signal and Power Integrity. This book was published in 1990s. Even people never thought of a power integrity. Father started, son completed the book actually. So this is very interesting book. And then there are, now I'm going faster and faster on the speed.
No problem.
Now if you do a high-speed digital design, this is called as signal integrity, just called as signal integrity. Okay, this is a very good book. This book, they show capacitive on one page and inductive on the adjacent page. So that's how they have done it. And of course, this is the final of all signal integrity. You can call it as a Gita, Bible, and whatnot. That's it. If you go towards, say, microwave and RF, sometimes we put RF and high-speed digital on the same board. Maxwell equation come into picture.
Correct.
So, having said that, signal integrity is in the 1980s, it was a Wild West. And then it became some sort of a science. But now signal integrity is engineering. What it means is you can weigh and measure it actually. There are still some other fields where it is very difficult to measure them. But here, the cause and effect and what if you implement it can be measured instantly. So with that, thanks. And I want to tell you one good word about signal integrity, which we are experiencing now. We are conducting this live show on a Deepavali day. There is a lot of crackers.
Fireworks is going
on. I think none of the audience heard it because our AV technician was using video and broadcasting protocol developed earlier by National Panasonic, and now it is, I think TI is controlling it. And I mean, that is the one which filtered all the noise. And if people enjoyed this without a glitch, even I had some delivery problem here because people were putting
lot of fireworks. Yeah,
there were a few skips here.
Excellent, Mr. Ambaprasad. Thank you very much for your time today. And thank you all the audience for watching this show. And every Friday, Global Electronics will bring one such guest who will talk about the expertise. And of course, we will have Mr. Amba Prasad more on the show on talking about various design aspects which is engaged in the electronics manufacturing side. Having said that, one more thing I wanted to mention here is signal integrity is definitely an important feature in our day-to-day life. As Mr. Amba Prasad pointed out, a live example. Currently, India is celebrating Festival of Lights, which is the largest festival which is being celebrated in India. And in this particular festival, there are a lot of fireworks goes on for almost few days. And as he mentioned, there has been a lot of fireworks on his background, which was going on even now. But we, as audience, or we definitely couldn't hear that, and that is a very good example of signal integrity usage in the audio or video system that we are using today. With that said,
Yeah.
please subscribe to the channel. Please share the channel link with your friends, colleagues, and the industry professional. And also, you can suggest people to participate in our talk show that way with their expertise. And so people are made more and more aware of the situations which are directly affecting in a positive or a negative way in the electronics manufacturing side. So, Mr. Amba Prasad, once again, thank you very much.
I have one more sentence
Yes,
to
please
say.
do. Yes, sir.
When telegraph was made earlier
Yes,
by Edison, nobody believed it can go such a long distance. Somebody
right,
asked him how it is possible.
right.
He explained scientifically, the person didn't understand. Then he told the telegraph system has the longest dachshund dog available. Imagine, a longest dachshund dog. He said, in New York, you pull his tail. In London, it will bark. So, that this was told by Edison. And now, signal integrity is something similar. And
Yeah.
now we are able to talk across the continents, across the time zones, and things like that. Yeah, that's it. And yeah, a happy Deepavali from Bengaluru also to all of you. See
Thank
you
you
next
very
time.
much. Thank you very much, Mr. Amba Prasad. And thank you, Mr. Sandeep Sadanandappa, who is definitely a technical backup for all our shows. And once again, I thank you for being there at the given time. And you all take care of your health, and please catch up with us on next Friday at the same time. Oh, don't forget, next Friday, our daylight saving time ends, and we will be keeping our clock 1 hour behind. Of course, India time doesn't change, but US time would change. Instead of 9:30 a.m., we'll start at 8:30 a.m. With that said,
What is next week? Can you announce now?
yeah, next week, no, I need to keep it little secret, and I will say
That's
that
good.
in 2 days.
I'm looking
Yes,
forward for
yes, in 2 days. Yes, yeah.
Thank you.
So we will announce that. With that said, we will sign off today's show here only, and keep watching Global Electronics for electronics manufacturing knowledge. Thank you very much.